Hey, welcome back. We're now in chapter 4 where we're working with higher order linear differential equations. And here in the beginning we have 4.1.1. We're going to talk about initial value problems and boundary value problems. Okay, so for the kind of section this 4.1 up into, I believe, 3 parts. Okay, so just so you're aware. Anyways, 4.1.1, initial value problems, and then these other things called boundary value problems. Okay. So what we're working with here are nth order differential equations. In particular, the form is this thing. And we've kind of seen this before with regards to first order linear differential equations back when we did the integrating factor problems. Okay, so it's basically just that, but now with higher order. Okay, so anyways, nth derivative of y plus a sub n minus 1 of x dn minus 1y over dx n minus 1 plus dot 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 plus a sub 1 of x times y prime plus a sub 0 of x times y, and then you have some other function on the other side, g of x. Okay, so this is the guy we want to work with in this section, chapter 4.1, section 4.1. So you got to, we'll have to develop some other ways of talking about it so we don't have to write this big thing out every time we talk about it. And the way you'll see it in the book later on, and I'll just kind of let the cat out of the bag, is we'll describe it as L of y equals g of x. Okay, so this L thing is a polynomial operator. So you kind of pretend like this whole thing can be I don't know, applied to a function. Okay, you're just taking a function and kind of putting in the derivatives, and yeah, but we'll get there eventually. We'll have this notation instead. Here we're working with an initial value problem or boundary problem. For initial value problems, you'll have n initial conditions. So you'll have like y of x sub 0 equals y sub 0, y of y prime of x sub 0 equals y sub 1, all the way down to the n minus first derivative, the n minus first derivative of x sub 0 equals y sub n minus 1. Okay. For the initial value problems, so long as the a sub n functions, these coefficient functions, are continuous, as well as the g of x function, if that's continuous as well, and the leading term, the leading coefficient function, a sub n of x, is not equal to 0, then you're going to have a unique solution. And that mirrors what we saw for the first order linear differential equations with the integrating factors. We had to presume that function p of x and f of x were continuous. We didn't have to worry about the non-zero part because of the way we formed that guy. So if you recall the first order linear differential equations, maybe we had something like, recall for example, x dy over dx plus y equals e to the x, something like that, right? So when we did those problems in that context, we would have to first divide out by x. We're not going to do that anymore. We're just going to kind of leave it as it sits. And then for this thing to have a unique solution, we require the coefficients here to be continuous. So we want, now we want x, the coefficient on y prime, 1, the coefficient on y, and e to the x to be continuous, and x to not equal 0. Okay. So in general, what you'll see that in the book as theorem 4.1.1. Okay, so section 2, existence and uniqueness. And generally, we kind of just assume this to be true. Don't make a big deal out of it. But here we go, theorem 4.1.1. So basically, we need those a sub n things, a sub I of x functions and g of x to be continuous. So we need this a sub n of x, comma, a sub n minus 1 of x, comma, dot, 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 comma, a sub 0 of x, comma, g of x to be continuous. And we need a sub n of x to not be equal to 0. And when all that holds, then this equation back here, let's call this equation number 1. That equation has a unique solution. Okay, but what I'm saying is you kind of already seen this issue before when we dealt with the integrating factor problems. That p of x and f of x being continuous was kind of the same deal as what we're doing here, except we're not dividing out by that a sub n of x. Okay, let's look at the homework problems and see if there's anything along. I don't think they have any real questions along these lines in the homework. They might. I don't remember it though. So, oh, here's one. So find the largest interval, which includes x equals 0 for the given initial value problem. So we have x minus 4, y double prime plus 2y equals x. And they give you some initial conditions. But the only important part of the initial conditions is the x value. We need to make sure that our interval that we pick includes that value. So y of 0 is 0, y prime of 0 is 1. So the functions, the a sub n junk that we're worried about, in particular a sub 2 of x, would be x minus 4, or actually that would be, yeah, that's a sub 2. And then a sub 1 of x is just 0, and then a sub 0 of x is 2, and then our g of x is just this x thing. You don't have to note which a sub whatever it is. It's just, note those 3 functions. The first one is continuous everywhere. The second one's continuous everywhere. The third one's continuous everywhere. But then you also have to make that other condition here. Whoops, I said it's not equal. It can't be equal to 0. I'm sorry. That should be not equal to 0. That condition has to be met as well. So you need to take this a sub 2 of x and set it equal to 0 and find the x values where it's equal to 0, so you can exclude those. So x minus 4 is 0. In other words, x cannot be equal to 4. So our interval of definition is going to be either in the interval from negative infinity to 4 or 4 to infinity. You go back and look at that x value, this x equals 0. That value is in this interval, so that is what you pick as your interval of uniqueness and definition. It seems like they used to call that I sub 0 at the beginning of the book, and then they just started calling it I, but I'll use I sub 0. Okay, so there's really only one question with regards to that issue, and then they leapfrog from there and start talking about boundary, initial value problems and boundary value problems, okay? So the deal is initial value problems won't necessarily have this existence uniqueness thing. So theorem 4.1.1 is going to applies to IVP, but not the BVP. Okay. So what is a BVP? Anyways, it's kind of just like the initial value problems, except instead of giving you y of 0 equals 0, y prime of 0 equals 1, they'll give you something like y of 0 equals 0, and then y of pi equals 0. So you'll get 2 initial values in on the same function, your solution, on your solution. Okay, so let's kind of, number 4, they'll kind of go back and forth between the different types. So for number 4, they use the solution c1 e to the x cosine x plus c2 e to the x sine x, and our differential equation, which turns out not to be necessary for our purposes, but we'll list it anyways, is this thing. Part A is an initial value problem. So y of 0 equals 1, and then y prime of pi equals 0. Right, so to solve this, you just take the original equation, plop in y of 0 equals 1, and then find its derivative and plop in 0 pi, or pi 0 rather. Okay, so the original function y equals c1 e to the x cosine x plus c2 e to the x sine x. Plugging in this first initial condition, we get 1 equals c1 e to the 0 is 1, cosine of 0 is 1, so just c1. Sine of 0 is 0, so you just get c1 is 1. Then let's get the derivative of this function. So that's, you got to do product rules. The first one I'll leave cosine alone, the derivative e to the x, just e to the x, and you get cosine x. Plus, now take the derivative of cosine, so that would be a negative sign, so you get minus c1 e to the x, leaving e to the x alone, sine x, plus c2, so the derivative e to the x is e to the x, leave sine x alone, and then plus c2, leave e to the x alone, the derivative of sine is cosine. Okay, and then we could plop in our second initial condition here. So the output will be 0. I'm inputting pi, so I'd end up with c1 e to the pi. Cosine of pi is negative 1, so I have negative c1 e to the pi. Sine of pi is just 0, so anything with sine is going to be 0. And then the last term, minus c2 e to the pi. Cosine of pi is that negative 1, so it's already kind of encoded there. Okay. I'm going to take c1 equals 1 and plop it in here, do a substitution. So I have 0 equals negative e to the pi minus c2 e to the pi. Okay, solve for c2, so add c2 e to the pi to the other side. Divide both sides by e to the pi, and I get c2 is negative 1. So my particular solution in that case, y would equal c1, which is 1, e to the x cosine x, then minus 1 e to the x sine x. Okay, and that solution will be unique. The actual interval that we'd be working with for uniqueness of solutions is negative infinity to infinity. If you look at the differential equation here, the leading function, the thing in front of y double prime, if you wish, a2 of x is 1, a1 of x is negative 2, a0 of x is 2, and then our f of x or g of x, whatever they called it, is 0. All those functions are continuous, and on top of that, a sub 2 will never equal 0. So the interval of uniqueness in this case is negative infinity to infinity. So you could be rest assured that that's the only solution that goes through that point. Okay. Anyways, boundary value problems you see in part B. So B, this first one is an IVP, and the second one's a BVP. We're not really going to be spending any time with BVPs. So hopefully I'm not misleading you thinking that this is a big deal. It's really not. It depends on which field you're going into, math-wise or engineering-wise. But we just show them to you so you get a flavor for them. For boundary value problems, you can have no solutions, you can have several solutions, you can have infinite solutions. Okay, even though the function is satisfying the requirements of this existence theorem 4.1.1. So anyways, you look at this problem, and we're using our given function y equals c1 e to the x cosine x plus c2 e to the x sine x. Okay. We're going to plop in those initial conditions. So first plug in 0, 1. So 1 equals c1, e to the 0 is 1, cosine of 0 is 1, plus sine of 0 is 0. So you just get c1 is 1. Then plop in the other initial condition, the pi negative 1. So you get negative 1 equals c1 e to the pi, cosine of pi is negative 1, so you get a negative right there. And then sine of pi is 0, so the other part is just 0. So you can solve for c1. C1 would equal e to the negative pi. Okay, and that's the problem, right? You can't have c1 equaling two different things. So those things together then imply that there are no solutions to this boundary value problem. Okay, so in the software, in the homework, you'll just write does not exist for your answer. Okay, okay. Part C, you'll see you can have one solution resulting from that also is a boundary value problem. Part D is the infinite solution case. So we can kind of look at part D. Again, it's a BVP. We have y of 0 is 0, and then y of pi is 0. Okay. So on your solution curve, it's just basically saying that your solution needs to go through this point, and then at 3.14 whatever, it needs to go through this point, regardless of what it does. In the meantime, it needs to go through those 2 points. It's kind of it's nailing down your function. Okay. Anyways, let's see if there's anything that works here. And again, working with y equals c1 e to the x cosine x plus c2 e to the x sine x. Plugging in 0, 0, you get 0 equals c1, and then plugging in pi, you get 0 equals negative c1 e to the pi. But if you solve for c1, you just get c1 is 0. Multiply both sides by negative, divide both sides by e to the pi. So the result here is that y would equal, the first term would just be a big 0, and then the second term is a c2 e to the x sine x. So you have an infinite number of solutions going through these 2 points. Okay. Okay, so boundary value problems, a little bit different. We're not going to spend any more time on that really, though. So let's move on. Okay, the next part is 4.1.2, and we're working with these homogeneous equations. Okay. In order to talk about these things, because we're going to be using this so much, we don't want to keep writing it out over and over and over. We're going to sort of adapt this kind of notation, this polynomial operator notation. Okay, but the overall idea here is that homogeneous differential equations are equal to 0. So for homogeneous, that g of x thing will just be a 0 on the right. You're going to then be able to solve these differential equations, the ones that have functions on the other side, by solving the homogeneous equations. So it's a weird thing that you can solve an equation like this guy, where you have a g of x on the other side. It's called non-homogeneous. You could solve that by solving the homogeneous version. So when this thing is equal to 0, if you solve that, which is easier, then you'll be able to solve the non-homogeneous. Okay. So anyways, first off, we want to introduce that new sort of definition for describing these objects. So we'll say that L of y is equal to, and then there's going to be another sort of definition here called a differential operator. And so I'm getting ahead of myself. So instead of writing y double prime, which in Leibniz notation would be d2y all over dx2. Instead of writing it like that, we're going to write big D2y. Okay. Okay, so you could think of the D2 as operating on this function y. You can almost think of it like it's a function unto itself. It's just the input of D2 is going to be this thing y. You basically put it into this D2 thing, and the D2 changes it into a different function by taking its derivative twice. Okay, so it's just a different way of writing non-derivatives. You may have seen it briefly introduced before, but we're going to use it kind of in this section, and then later on when we talk about annihilators, we'll use it again there. But anyways, we're going to rewrite that nth order linear differential equation using this new notation, this L notation. Okay, so L of y and the differential operator notation. L of y is going to be a sub n of x dn of y plus a sub n minus 1 of x dn minus 1 y plus dot 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 plus a sub 1 of x dy plus a sub 0 of x y. Okay, and we're not going to put the equal, it represents just one side of the linear differential equation. Okay, yeah, this thing is called, the L without the function in it is just called the linear, the polynomial operator. So if you just write L, you can think of that as a sub n of x dn plus a sub n minus 1 of x dn minus 1. And you're thinking of this polynomial operates on a function y. So you're basically putting the function y into this thing. And plus a sub 1 of x d plus a sub 0 of x. Okay. Okay, so this guy is called the polynomial operator. Anyways, we're going to talk about the nth order differential equations now using that notation. What it does is it allows us to not have to rewrite this a sub n of x dn plus a sub n minus 1 of x dn minus 1 all over and over and over and over, right? It just makes our life a lot easier. So if we want to write out then, and you don't have to write this down, but just for the sake of kind of putting it all together, if you wanted to write out the differential equation a sub n of x d n y all over dxn plus a sub n minus 1 of x dn minus 1 of y all over dx sub n plus dot 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 plus a sub 1 of x derivative of y with respect to x plus a sub 0 of x y equals g of x. In order to write that out, now we can write L of y just plain old equals g of x. Okay. This is called a non-homogeneous differential equation because it has that g of x on the right side. If L of y just equals 0, that's the homogeneous version. And right now, we want to kind of focus in on this homogeneous version. It turns out if we could solve the homogeneous version, it's only a couple more steps to get to the non-homogeneous version, because the non-homogeneous solution, in part, is the solution to the homogeneous. Okay. Okay. So what we're after then are solutions, in particular the general solution to these homogeneous equations, and that becomes another issue. So finding the general solution, basically we want the most compact solution possible to the differential equation. In building our solutions, we first encounter this idea of superposition, which you may have heard of in physics. Basically, if you're dealing with a force on an object, the force on an object is the sum of all the individual forces, right? And they consider that superposition. In our context, it's basically if you have a bunch of solutions to a differential equation, you can add them together and multiply them by constants, and there'll still be a solution. And that's basically theorem 4.1.2. 4.1.2, and it says if y1, y2, y3, all the way up to yk are solutions of this nth order linear differential equation, L of y equals, and it's homogeneous, so it equals 0, then the linear combination of all those guys, in other words, y equals c sub 1, y1 plus c sub 2, y2 plus plus c sub k, yk. This thing is also a solution. Okay. And it follows from the linearity of the differential operator. It's something that you're kind of aware of from just taking Calc 1. Basically, if you read kind of their explanation in the book, you kind of, and then kind of recall how derivatives work. The derivative of a sum, like maybe you have like 3x squared plus 5x, you could find the derivative by taking the derivative of the parts. So the derivative of the sum is the sum of the derivatives. Okay, so that's the first part of linearity. The second part of linearity is the constant multiple rule, where you can always factor constants out of derivatives. Okay. 5d dx x. So it's because of that linearity property that theorem 4.1.2 is going to end up being true. Because if you think about it, this L of y thing, this this polynomial operator is just a huge derivative thing. So if you know these guys are solutions, and you have then, let's say for example, y1 and y2 are solutions. Suppose y1 and y2 are solutions of L of y, then you can kind of consider L of c1 y1 plus c2 y2, because this L thing is just a huge kind of derivative thing. It'll obey those same rules of derivatives, that linearity property. So you'll end up with L c1 y1 after you kind of like, the L of a sum of functions is a sum of L of those functions. And then you can factor out the constants. You get c2 L of y1, L of y2, excuse me. This part is 0, and this part is 0, because they're solutions of L of y equals 0. So when you plug y into L, you just get 0 out, because they're solutions, right? So that will be 0, and that will be 0. C1 times 0 is 0. C2 times 0 is 0. So that will equal 0. In other words, this thing is a solution to L of y equals 0 as well. But it's all dependent on the properties of the derivative. Okay, so that's a superposition principle. There's a couple corollaries that go along with that. I think are kind of obvious, so I'm just going to leave that to you. Okay, so the next part is we want to find kind of the general solution of these differential equations. So we're going to pretend somebody gives you a bunch of functions, okay, that are solutions to this differential equation, and some of them might be redundant. Okay, so for example, let's look at number 15. Okay, so this section we're going to say is finding the general solution. Solution to the, we don't have the tools to do this yet, but we'll just pretend somebody's giving you a bunch of solutions. How do I, throw out the ones that are kind of redundant? I just want the perfect solution. I want to be able to write out the solution in as few symbols as possible, and it should describe every possible solution in the solution universe. Okay, so finding the general solution, and we'll look at number 15. So let's say somebody has been working on this differential equation and found that y equals 1 equals y1 equals x is a solution, y2 equals x squared is a solution, and then y3 equals 4x minus 3x squared is a solution. Okay. I want to get rid of the riffraff, get rid of the stuff that doesn't really need to be there, so I have a compact form for my general solution. And the way you can do that is if you can find constants C1, C2, C3, such that when I multiply these solutions by these constants, I end up with a 0. And you have to assume that these constants are not all 0. So this is from definition 4.1.1 now. We're talking about these ideas of linear dependence and independence. Okay. So if you can find C1, C2, C3, not all 0, such that the sum equals 0, then one of the solutions is redundant. Okay, you don't need it, and one solution at least is unnecessary for our purposes. Sorry, I don't know how to spell necessary apparently. And in that case, when you have a solution that's unnecessary, the overall set of solutions will be called linearly dependent. If you've taken, and this is where taking like linear algebra would be really helpful, because you would understand that idea of a basis for your vector space, and it's basically that idea. You want the smallest set of objects to describe your space. Okay, the smallest set is a linearly independent set, and you may have heard it when you were solving systems of equations as well. So, for instance, we can make this kind of well. Before I get ahead of myself, let's just find the C1, C2, C3 such that when I add them together it equals 0. And clearly you could put 0 in for C1, C2, C3 and it would equal 0. But note it says not all 0. Okay, so if they're all 0, then nobody cares. That's trivial. We need to find ones that are all not necessarily 0. So you could pick. So let C1 equal -4, C2 equal 3, and C3 equal 1. So in that case, we note -4x plus 3x squared plus 4x minus 3x squared, of course, equals 0. And hence that set of solutions there is not linearly independent. It's linearly dependent. And therefore, it's not going to be that perfect set that we want for our general solution. Okay. Okay, so again, this idea of linearly dependent versus independent. So linear dependent versus independent. So another example, you could just work with equations of lines. So maybe you have one solution is 3x plus 2. You have another solution is 3x, and then you have another solution which is and I don't want to write it explicitly. So let me get rid of these y sub 1's. Another solution, which is 9x minus 3y equals negative 6 or something. Okay. So I want to know if these guys are linearly dependent or are they independent. Okay. And you know they're all lines. The question is, are any of them basically the same line? Right? And that's very similar to what we're doing, but then we do it with other types of functions as opposed to just lines. And you probably saw this when you're solving systems equations with 3 equations, 3 unknowns, and you would end up with infinite solution cases. But anyways, here, are there any that are unnecessary to this picture? So if you look at this guy here and you rewrite it a little bit, move the 3y to the other side, and you have 9x, move the 6 over, plus 6, divide by y, and you get 3x plus 2. You see these two equations are exactly the same thing. So this guy is not necessary. In other words, the whole set of these 3 functions you can think of as being dependent. Okay? Once you get rid of that guy, you just have these 2 functions which are kind of different from each other. They're parallel, they're different from each other though. And then you could say that potentially these describe your solution space. Okay, let's change that so they're not parallel, but let's make them kind of negative 3x, something like that. Okay. All 3 together are dependent. Once you kick out that last one though, then these 2 are independent. Okay. And I think that describes kind of the situation we're in. The general solution is going to be an independent set of functions. So you'll be given these sets of functions. You want to figure out if they're independent or dependent. If they're independent, they're kind of, you can use them to form your general solution. If they're dependent, you need to kick out a couple of these guys until you have an independent set of functions, and then you could do your general solution. Okay. One point to make: the general solution of an nth order differential equation is going to have n functions in it. Okay, so one small point I think I missed in my exploration here usually is that nth order differential equation that we've been dealing with, these homogeneous, L of y equals 0, has n functions in its general solution. Okay, I think we can kind of look at a couple of these. So in particular, number 5 is just like the one example I was just doing. Let's look at maybe number 7. Okay, so they're giving you sets of functions, a set of functions, and you have to figure out if they're linearly dependent or independent. Okay, is there any riffraff in there? For ones that have like trig functions in them, you can usually figure out the constant. So C1, Y1, so we have C1 times 2 plus C2 times cosine squared x plus C3 sine squared x, and I'm trying to find some constants that are not all 0, such that when I add these guys together I get 0. So in particular, you could usually replace cosine with 1 minus sine squared, and then you'll probably be able to get to your answer. So let C1 equal 1/2, C2 equal 1, and then C3 equal 1, and see what happens. So in that case, you would get 1 plus, replacing cosine squared with 1 minus sine squared, like that, and then plus sine squared And yeah, see, you got that. Whoops. How about a minus 1/2? There we go. Yeah, so that would be 0. So that implies that they're not independent. Okay, they're not good. So I'll say they're linearly dependent. Okay. In this process, it proves that they're dependent, because if you can find a constant that makes it equal 0, you can literally solve for one of the functions in terms of the other functions. Okay, and in that case, that means that you can eliminate that third function altogether and reduce your solution set. Okay. Sometimes it's going to be really, really difficult to kind of figure out those C1, C2, C3 constants to show that it's dependent or independent. So what the book does is give you this thing called the Wronskian. Okay. And where is that in the book? So the Wronskian, there it is. So definition 4.1.2. This Wronskian thing is a linear algebra thing. We have to work with determinants in order to figure it out. So let me introduce the Wronskian sort of as a whole new section. We're in section 3. Yeah. So I put a 4 and write out the Wronskian. And you could always use the Wronskian to figure out this issue. You don't have to guess, but sometimes the Wronskian can be a lot of writing. So if you look down here at the Wronskian, it's kind of nasty sometimes. So you might want to avoid it in certain cases, but here we go. First, just how does it work, or how do I compute these things? The operation is a determinant operation. And it's it's just a way of combining numbers in order to produce a new number. It's from linear algebra, and it's about solving systems of equations, essentially. You're determining if a system of equations can be solved for certain coefficients. And in the case that it can, you'll end up with a determinant that's not equal to 0. Okay. And that would be a good case. If it turns out that your Wronskian is equal to 0 for all x's, then that's bad. That means they're linearly, they're probably linearly dependent. Okay, and we kind of need to throw out the riffraff. But anyways, how do I do this computation? So we just want to look at some examples. First, a 2x2 determinant computation: 1, -1, 3. In order to do this, what you're going to do is multiply 2 times 3. So it's purely just computation. No rhyme or reason for you at this point. If you're more interested, take it, the linear algebra class, and you really get in there and figure out what these things are. Anyways, 2 times 3, and then minus the product of the second diagonal. So that would be 1 times -1. Whoops, let me go back to black. 1 times -1. I think the appendix in the back of the book will show you how to do determinants if you're still not on board by the end of this exploration. So anyways, we got 6 minus -1, which would be +1, which is 7. Okay. You could do determinants with functions. So you say you have x and then 1 and then x squared and 2x. The determinant of that thing will be x times 2x, which is 2x squared minus, so it's always minus, x squared times 1. So x squared times 1 is just x squared. So 2x squared minus x squared is x squared. Okay, that's the 2x2. Then 3x3's determinants are a little more complicated, but if you know how to do the determinant operation, you could do a 3x3, no problem. So let's do 2, 1, 2, 1, -1, 1, and 3. 2, 3. Okay, so how does this work? First, you're going to write down this number, okay, this 2, and then you go parentheses, and in here, you're going to put this determinant, the determinant of this box, okay? So it's kind of like you're covering up this row, this column, and this row, and then find the determinant of the box, okay? So the determinant of that box is going to be -3 minus 2. Okay, so -3 minus 2. Then the next term is always negative. You're always going to put a minus there. Okay, let me erase all this. So first, initially, you write down this number 1. Okay, so you have 1 times. Then your determinant is going to be the result of covering up this row and this column. So you use the 1, 1, 3, 3 as your box, so to speak. So you're going, in this case, 1 times the 3 minus, so 1 times 3 is 3, minus 1 times 3, which again is 3. I'll put that in black. And then the last ones, let me erase stuff again. I'm going to circle that first number in the row, the 2. Okay, so the last portion is plus 2, and then times the determinant resulting from kind of covering up this row and this column. Okay, so our determinant now is in this box. So I go 1 times 2 minus -1 times 3. Okay, so 1 times 2 is 2, minus -1 times 3 is -3. And then I go and evaluate this. So 2 times -5 minus 1 times apparently 0, plus 2 times 2 plus 3 is 5. And I get 2 times -5 is -10, plus 10, which would equal 0, which would be bad. Right? That would mean it would be linearly dependent, and so we would need to kick out the riffraff. Okay. We could do this also with functions, so let's do a function version. And the way we're going to be setting up our Wronskian is kind of as follows. Let's go ahead and work with this example I had introduced. Right, yeah, sure, let's do this one. The y1 is 2, y2 is cosine squared, y3 is sine squared. Okay, so let me erase this a bit. So y1 is 2, and then we had, I think, sine squared, and then cosine squared. Okay. To build this 3 by 3, what you're doing is taking derivatives as you go down the column. So derivative of 2 is 0, derivative of 0 is 0. Derivative of sine squared is 2 sine x times cosine x. The derivative of cosine squared x is going to end up being -2 cosine x sine x. Okay. And then another derivative, I have to do a product rule, so it's going to be -2 sine squared x plus 2 cosine squared x. And then this last position here, taking the derivative going down the column, is -2 cosine squared x plus 2 sine squared x. Okay, so you can see these can kind of be nightmarish. Okay, so for the first part, I need to first write 2 down. So I'll have 2 and then times the determinant of this box, right? So I'll have this times this and that minus that times that. So the first multiplication, I'll have -4 cosine, oops, let me go back to black. So -4 cosine cubed x sine x plus 4 sine cubed x cosine x and then minus, this will be then distributing this negative. We're going to have 4 cosine x sine cubed x minus 4 cosine cubed x sine x. That's pretty nasty. Then the next term minus, and this time we are taking sine squared in front. So we have sine squared x. And then the determinant will come from these parts, right? So 0 times 0 is just going to be 0, this part, and then 0 from that part. So 0 minus 0, so that's not too painful. I'm trying to get it in black. 0 minus 0. And then finally the cosine squared part. So you'll write cosine squared first, so plus cosine squared x. And then the determinant of this portion is just 0 again, 0 minus 0. Okay, so the main answer is going to come from that first portion. Let's go ahead and evaluate that. So it'd be 2 times, and you can see everything's going to cancel out. So this negative 4 cosine cubed sine x, and then you'll have a positive 4 cosine cubed sine x canceling with that. 4 sine cubed cosine x minus 4 sine cubed cosine x, they're all 0. So in this case, it equals 0 for all x. And therefore, the set of solutions given here is linearly dependent. So that's kind of the bad case we want to think of it. It's not able of living on its own, right? It's not independent. It's not independent from its parents yet. So this is not linearly independent yet, as far as I can tell. So that brings us to 4.1.3 then, which basically says you can use the Wronskian to test a set of solutions to see whether or not they are a nice independent set. Okay? So theorem 4.1.3 says if you put all of these solutions into the Wronskian, so pretending that W of these solutions is basically you're putting these y1, y2 into a big matrix kind of thing, like above. And I'm not going to harass you with any like 4x4s or anything. Oops, y3, y4, etc. So if you put those into the Wronskian and they end up not equaling 0, then it's linearly independent. And the solution set is linearly independent. Okay. So they give you an example of the book that's kind of nasty. Let's look at something from 4.1. They kind of force you to do Wronskians on certain problems. Some of them are rather nasty. Let's look at number 10. Okay, so the solution set y1 is e to the negative 2x, y2 is e to the 3x, and then we have our Wronskian is going to be e to the negative 2x, e to the 3x, and then you just take the derivatives going down the columns. So e to the negative 2x times negative 2, e to the 3x times 3, and then boom, boom. So you get 3e to the 3x times e to the negative 2x. You add the exponent, so you just get 3e to the x plus, or rather minus, negative 2e to the negative 2x times e to the 3x. Again, add the exponents, you just get e to the x. And at the end of the day, it'll be 3e to the x plus 2e to the x, which will equal 5e to the x, which is not equal to 0. So in this case, we have linearly independent set hence the set is linearly independent. And if you look at our differential equation there, it's second order. And then if you remember what I said back here with the star, nth order differential equations have n functions in its general solutions. So we have two functions that are linearly independent. That means we can form the general solution from which all other solutions will emanate. Okay, so our general solution is then y equals, and you just take the two functions and slap some constants on them. c1e to the negative 2x plus c2e to the 3x. Okay. So we got some more Wronskian problems. Okay, the last part then we get into the non-homogeneous version of the issue. And so let's take a look at that. 4.1.3 now. The non-homogeneous equations. So instead of L of y equaling 0, we have L of y equals some function g of x, right? So where L of y, if you remember, was the L of y is the left-hand side, this thing. That's L of y. If it's equal to some function g of x, if you have L of y equals g of x, that thing is non-homogeneous. Sorry. If L of y is equal to 0, that's considered homogeneous. Okay, so this next part is saying that if you can figure out the solutions to the homogeneous part, it's not too far to get to the solutions to the non-homogeneous version. Okay, so let's take a look at this part. Non-homogeneous equations, so looking at what is the general solution. Basically, the general solution will be y equals the general solution of the homogeneous equation, which will look like something like C1, Y1. So if you have an nth order differential equation, it'll have n functions describing the general solution. C2, Y2 plus da 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 plus Cn, Yn, and then plus some particular solution to the non-homogeneous version. Okay, so this thing here is the general solution like we've been finding above. It's the general solution to the homogeneous equation. This thing is just some randomly found solution to the non-homogeneous. Okay, so this is any solution to L of y equals g of x. Okay. In particular, we call that first part the complementary function, and we'll call it y sub c. And then the second part is just the particular solution. Okay, we want to kind of prove that this is the fact, that this is the case. Okay, so let y of x be any solution to the non-homogeneous differential equation L of y equals g of x. Let then y sub p of x be some other solution, or be some solution to L of y equals g of x. Then notice, or then consider this function u of x formed from the difference of y of x and yp of x. Okay. Note what happens to it when we put it into L of y. So when we push it into the polynomial operator. So L of u of x from the linearity property of the derivative is going to end up being L of y of x minus L of yp of x. And then because we know that y of x and yp of x are solutions to the non-homogeneous equation, these guys must both equal g of x. So you get g of x minus g of x, which equals 0, which implies that u of x is a solution of the homogeneous equation. U of x is a solution to L of y equals 0. Okay, so what? Well, then you could describe u of x using the general solution to the homogeneous equation. So thus, u of x, which is really just y of x minus yp of x, is, you could set it equal to some version of the general solution to the homogeneous equation, that y sub c thing from above. Okay, you could describe it using this. Okay, so y of x minus yp of x is going to be equal to y of c, and then you could solve for this unknown y of x in terms of y sub c and y sub p, okay, which kind of goes to show what we were trying to show. And that's it. Okay, so it's this weird kind of proof thing. I think it leaves it seems too good to be true, and it kind of just is so simple it goes over your head, but it really is just that simple. Anyways, we'll be using this fact later on when we actually have the methods to solve these differential equations. We'll be looking for this complementary, this general solution to the homogeneous equation, and then just kind of pairing in a particular solution. And yeah. Okay, the last section in here is kind of the non-homogeneous version of superposition. And let's see where it is in the book. Yeah, so it's down here. You see it kind of in example 11. So what it works like in this case, we'll say we have different particular solutions. So y sub p sub 1 equals negative 4x squared is solution to y double prime minus 3y prime plus 4y equals negative 16x squared plus 24x minus 8. And then let's say we have yp sub 2 equals e to the 2x is a solution to, and the L of y changes, or not the L of y, but the g of x changes. So we have y double prime minus 3y prime plus 4y equaling something else like 2e to the 2x, okay? And then let's say we have a yp sub 3 is equal to x e to the x, and that's a solution to this L of y equaling this other g of x. Okay, so in this case, 2x e to the x minus e to the x. So is there a way to kind of combine those solutions into one kind of mega solution like we did with the homogeneous differential equations? And it turns out, yeah, sort of. So it'll turn out that y equals negative 4x squared plus e to the 2x plus 2e to the 2x, or rather plus x e to the x is a solution to a different differential equation, which on on the right-hand side has the sum of those three different g of x's. Okay. It'll be a solution to this L of y double prime minus 3y prime plus 4y. But on the right-hand side, it has to be negative 16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. Okay. And that's kind of the superposition principle. You don't really get into it too much in the homework. Maybe like in the last, the second to last problem, you kind of look at it. So number 14 is definitely challenging in that you kind of have to guess at the solutions to the differential equation y double prime plus 2y equals 6. So if you think about the trig functions, they kind of will cancel each other out if you look at their derivatives. Yeah. So if you have y equals something like sine of x, y prime is cosine x, and then y double prime is negative sine x again, right? So if you had something like y double prime plus y equals 0, you would know that y must equal sine of x. Okay? This differential equation is very similar, right? So you can kind of take advantage of the chain rule and let your y have some element such that when you do the chain rule, it's going to equal 2 out in front. Okay, so you'll be able to get a nice cancellation of the sine part, but you'll still have this other part. You need it not to equal 0, but rather something else, right? So if you just let y equal, in this case, sine of square root 2x plus 3, it'll satisfy that equation. So you really have to kind of play around with it a little bit, and it helps to have a lot of experience like your teacher has. You may not have as much of experience, but anyways, hopefully that will get you started on number 14. You can kind of see what I did here on the right. You may want to pause the video and run over there and do number 14. But okay, we'll leave it at that for now. I'm sorry that this video is a little long. They kind of squished 3 sections into one. There's a lot of theory in there, but at the end of the day, all we're doing here is trying to find this one perfect general solution from which you can get any solution in the universe. We want our solutions to be compact, so we don't want any redundant functions. So in order to make sure that our solutions are compact enough, our general solution is compact enough, we use the Wronskian. We don't really know how to solve these differential equations yet, right? We're just kind of still, we're being given these formulas from above, we're given the solutions from above, and we're kind of just looking at the solutions, playing around with them. Yeah. Okay, so don't lose track of the big picture in this section. The waters run pretty deep, and there's a lot of logic involved. But okay, we'll leave it at that. Thank you for watching. See you next time.